Okay, then we can start, I guess. It's time. So I first of all wish everyone happy Independence Day today. And yes, now we can start. And hello, I'm SHAKSHI Bhardwaj. I am a PMRF scholar under Professor Pradeep Kumar Maji in Department of Polymer and Process Engineering in IIT Roorkee. And I'm a course coordinator for Polymer and Process Engineering course under Professor Shishir Sinha in Chemical Engineering Department, IIT Roorkee. And this is the assignment 4 related problem solving session 4. As a brief introduction of mine, as I already told you, I'm Sakshi Bharadwaj. I'm a PhD scholar in Department of Polymer and Process Engineering in Institute of Technology, Roorkee. I'm doing PhD under Professor Pradeep Kumar Maji, and the topic of my PhD is fabrication of cellulose-based aerogels for thermal management applications. I have did my graduation from University of Delhi and master's from Maharishi Dayanand University. Apart from it, I have already conducted 2 projects, one in Indian Institute of Technology, Roorkee, over the aerogels, and another one in University of Delhi over repurposing of drugs for SARS-CoV-2. So this is the 4th session of Polymer Process Engineering, and in this session we are going to cover heat transfer topic and the questions related to heat transfer. So before starting, let us understand what is heat transfer, or what is the phenomena related to heat or heat transfer. So yeah, heat transfer is the process of thermal energy moving from one object or system to another due to a temperature difference. So it's like from moving to hot surface to cooler surface. So the transfer of heat from one surface to another, from one system to another system due to temperature difference. It's known as heat transfer. And there are generally 3 phenomena or 3 terms we can study in heat transfer: conduction, convection, and radiation. So what is conduction, convection, and radiation? Yes. So first, as you can also see in this picture, this is the pictorial representation of conduction, convection, and radiation. So here is the phenomena for conduction. So conduction is a heat transfer through material without any bulk motion of material itself, or I can say the heat transfer between solid substrates. So from the handle to the hand, because of the temperature difference, the heat is transferred from here to here, and this phenomena is generally known as conduction. On the other hand, convection is the movement of a hot fluid. So in this case, fluid or gases flow due to the convection phenomena, and here warmer and less dense fluid rise while cooler and dense fluid sinks, creating a cycle. For example, when boiling water in a pot, the heated water rises and the cooler water sinks. So it creates a cycle, like the heated water goes up and the cool water goes down. So it's a cycle in which fluid or gases generally transfer heat through this, and the phenomenon is known as convection. And the third one is radiation. So radiations are like heat transfer through electromagnetic waves. Sun warming the earth is an example of radiation. So through radiations, the heat is transferring from one system to another system. So this is radiation. So these 3 terms are very important when we read the heat transfer: conduction, convection, and radiation. So let us start with the questions based on this topic. And the first question is, in natural convection, the primary cause of fluid motion is viscosity difference, density change due to temperature difference, surface tension effects, or heat conduction through solids. So they are asking about the natural convection. What is the primary cause of fluid motion? Why fluid flows? Okay, I'm getting answers. And yeah, we just read this question just a moment ago. What is convection is and how the fluid flows. So I do not guess that it is a uh, difficult question. Yeah, it's an easy one. So yeah, the answer is B, which is density change due to temperature difference. And what we read is just the cyclic movement of fluids. And there's an explanation when a fluid is heated, it becomes less dense and rises. And cooler fluid, being denser, sinks to take its place. So this creates a circulating flow pattern, transferring heat through the fluid. So it's like the hot water, which is below the surface going up, and the cool water or cool fluid, which is above due to density, goes down. So it's create a circular motion like this. And due to this density difference, the fluid flows in natural convection. So the correct answer is B. And this is a very easy question, I guess. So it's not a typical one. Let us take another question then. Okay, so before question, let us read some more terms into this. And here, the first one is thermal conductivity. As we talking about heat transfer, so there are some more terms which is very relevant to this topic. But first is thermal conductivity, and which is thermal conductivity is a material ability to conduct heat, specifically how quickly it transfers heat through itself. So it's like how material can conduct heat. So this is the conductivity, the thermal conductivity, and any kind of material like solids, fluids, or something. And as we are talking about polymers, so in detail, we will talk about polymers itself, the conductivity of different polymers. But here, the thermal conductivity is a material ability to conduct heat. And this is you can see this as a material or a solid in which the heat is flowing from one end to another end. And here the temperature is different from there, here to here. There's two different temperature and the thickness of material and area. So there are some measuring parameters which is required to calculate the thermal conductivity. And this is the formula to measure thermal conductivity in which Q by delta T, where Q stands for heat, delta T stands for change in time, and thus K stands for thermal conductivity, where A is cross-sectional area, delta T is change in temperature, and L is the distance between the hot and cold reservoirs. So this is the formula we can use for calculating thermal conductivity, and this formula you can see that dependent on the length of the material, the area of the material, the temperature difference of the material, and the heat and the change in time of the material. So all these parameters are required to calculate the thermal conductivity. And one more important thing in the heat transfer is thermal diffusivity. And thermal diffusivity is a measure how quickly heat diffuse through a material. So it's the rate. In the thermal conductivity is the ability to conduct heat, but diffusivity measure the rate, how fast or how slow can one material pass the heat through it. And it's the rate at which temperature changes propagate through a material when subjected to a temperature gradient. So it's the thermal diffusivity is defined by this formula where alpha stands for thermal diffusivity, K stands for thermal conductivity, the rho is the density, and Cp stands for the specific heat capacity. So there are some terms which alpha depends on. And as in the previous section, we have already read about some numbers from in the viscosity section. Those who attended the session that should know that there was some numbers related to heat transfer, mass transfer, and viscosity itself. So here are some numbers which we are going to read, because on these numbers some of the questions and numericals based on. And the first one is the Fourier number. So it's the Fourier number FO tracks how far heat is diffused in the solid over time. So this denotes from F0 and it measures how far heat is diffused in a solid over time. So it's a number which depends on the time, and as we're talking about far, so it's like the distance or the length of the material. So it's given by this formula, which is alpha T by L square, where alpha stands for the thermal diffusivity, T stands for the time, and L square stands for length of the material. And the example for this Fourier number is like heating of a metal rod and cooling of electronics. So heating of a metal rod and cooling of electronics. So it's the distance phenomena which measure the distance, like how how much heat has transferred. And if we compare it with Biot number also we studied in the last class, which is measured the surface versus internal heat transfer resistance. So it's the ratio of surface and internal heat transfer resistance, whereas Fourier number is measured the how far heat is traveled internally. So we are reading all these numbers and the formulas because there are some numericals which are based on particularly these topics. That's why we are reading about these formulas. So I hope these terms like conduction, convection, radiation, conductivity, diffusivity is clear to all, because most of the questions depend on these phenomena and these numbers itself. If any one of you wants me to repeat anything, or it's no, diffusivity and conductivity are not same. They are different. And yeah, of course, the unit for all both of them is different. Heat conductivity is the material's ability to conduct heat. It's a different one. And diffusivity is the rate at which temperature changes or the heat propagates. It's two different phenomena. Conductivity tells us about that conductivity, increasing of conductivity and decreasing of conductivity also can tell us about gives an idea about how material behave. Like some materials have high conductivity and some materials have low conductivity. So it's there are different terms in the heat transfer, which I know that they are very confusing one, like the diffusivity, conductivity, specific heat capacity. All these terms relate to how material is transferring heat actually. But all these are little bit different in the definitions itself, and from all three we can calculate or we can find out different information itself. Like from the diffusivity, there's a different in the information, conductivity, there's a different in the information, and specific heat capacity, which we are going to read in the further slides, which is slightly different. Okay, are they limited to solids or they are applicable to liquids and gases? Of course, liquids and gases also have thermal diffusivity and conductivity itself. The solid and the gases phenomena are conduction, convection, which we have studied before. Like conduction is limited to solids, convection is limited to liquids and fluids, but conductivity and diffusivity also, yeah, we can find out the conductivity for solid itself, for liquids itself, or for gases itself. So these are the phenomena which we can find out for everything. So it's not actually limited to only solids or. Okay, then, if yes, we can move forward. And there's a question which is related to this we have just studied. The is if the thermal diffusivity of a polymer sheet is doubled, the heating time to reach a target temperature is. So they are asking about like if we double the thermal diffusivity of a polymer sheet. So what is the heating time? What will it be effect on the heating time to reach a target temperature? Either it will be double, it will be half, reduced by a factor of 4, or it will remain unchanged. I'm giving you 1 or 2 minutes to solve this, as it depends on the formula we just read in the last slide. Okay, I only got one answer. I'm expecting more. Okay, then. So yeah, the correct answer is B, which is half, and this is based on this formula we just read it, which says that Fourier number, which is a dimensionless number, and it says that Fourier number is equal to alpha t L square. So if we look at it, so it says that if alpha, which will be equal to L square t, and there is a Fourier. So if we see that alpha is inversely proportional to time. So here they are asking about the heating time. And because they have this inverse relationship, if the diffusivity of any substance is or a material is double, so that means that will reduce the temperature by half. So it's the simple phenomena, and the correct answer is will be B, which is the heating time to reach a target will be half. Yeah. So here it is the proper answer. The heating time or the time to reach a certain internal temperature during transient heat conduction is inversely proportional to thermal diffusivity, which is this is denoted by this formula, which is T is proportional to L square alpha, and there is an inverse relationship between T and alpha. So it says if T of alpha get double, so T will be half automatically. So it's not a typical question, it's an easy one. I hope this is clear to everyone. Let's move on to another question then. So this is a tricky question, not exactly tricky, but you need to take out your calculators, a copy, and a pen to solve this. It's like two identical 4 centimeter thick polymer slabs are bonded together with an adhesive that melts at 120 degrees Celsius. The press plate can be heated to 180 degrees Celsius given alpha, which is 2.2 into 10 raised to power minus 3 centimeters square per second, and F0, which is a Fourier number, is 0.0. So they are estimating the bonding time. They are asking the bonding time which is required for this. It's also a formula based question, so we can just simply put the formula and solve this question. Okay, I got the answer. I'm waiting for one or two more. Okay, then let's start with the answer. So the answer will be 1.4 hours, and the solution is like this. So here we have a formula which says F or Fourier number is alpha TL square. And here, because we need to calculate the bonding time, so the formula will be T is equal to F naught L square alpha. And as we have the value of F0, which is 0.03, L, which is 4 centimeter, and alpha, or which is 2.2 10 raised to power minus 3 centimeter, or we can convert it to meter square also. And this is the formula. We can just we need to simply put this into the formula and solve this question. There's nothing wrong in that. And after solving the question, the value we will get is 21818 seconds. And upon dividing it with 3600, the value will be 1.4 hours. Let me just check once more. 1818. Check with the calculations. I guess if there is a problem with the calculations. Yes, there's some problem with the options. Because on solving this question, I'm getting some different answer. Is it same case with you? Is it the time it takes for adhesives to melt? Yeah, two identical foam bonded together when an adhesive. Like this, please check the calculations because here from here it was correct, but as it will not giving the same answer to it, so I'm guessing it's getting a different answer. Yes, it's the time for it. It take for adhesive to melt. That's true. And little bit difference in the calculation. I guess from here, I am getting my answer on solving this 21.818. I'm sure you guys are getting an answer like this from here itself. Yeah, if yes, then we can change because it will not match with the answers then, because after on calculating this, and I'm getting a value of 0.06 hours with this. I'm sure if you guys taken out the calculator and solve this, you will also get the similar value, which is 0.06 hours, which is not in the, or which is somewhere similar to 0.7. I can say it will be, it really will not be the correct for this, and the correct answer should be A if we are talking about the similar one. So it's a simple question based on the formula. We just need to put the values in the formula, calculate the question. I hope this is clear. But it's a little bit mistake in this, because this solving this, that we will not get this answer 1.4 hours. So the calculations are a little bit wrong, and we are getting answers which is 0.06, or I cannot even say which is nearby to A itself, because it is 0.7, so it is very low. So it's the answer is 0.06 hours. Okay, then let's move to next. Yeah. So it's last phenomena and the different phenomena. I can say specific heat. We just read about thermal conductivity, diffusivity. Now we are reading about the specific heat. So specific heat, which considers the amount of heat energy required to raise the temperature of 1 unit mass. So it is also, you can see the conductivity, the diffusivity, and specific heat all related to the temperature itself, like how much heat is required in to raise something's temperature. But every definition has a different terminology and some different terms, or I can say a different phenomena in them. Like in the specific heat, it is specifically talking about mass. So here it is the amount of heat energy required to raise the temperature of 1 unit mass of a substance by 1 degree Celsius. Like what is the amount of heat required? So it is an intrinsic property of a material reflecting how much energy is needed to change its temperature. And the formula by which we calculate the specific heat is Q mc m into C into delta T. Q stands for heat, M stands for the mass, delta T stands for the temperature change, and stands for specific heat capacity. So here the specific heat capacity, the units for specific heat capacity is joule per gram per degree centigrade, which says the how much amount of heat required to raise the temperature of 1 unit mass by 1 degree Celsius. So it's in the unit itself, the definition of specific heat. And we will get some similar questions with the conductivity formula, with the diffusivity formula, and with the specific heat formula. So we need to check that what are the values we are given in the question and how we can calculate these terms from these. So let us take some questions over specific heat. So here's the question. Like a 2 kg aluminium block having Cp is equal to 900 joule per kg per Kelvin at 25 degrees Celsius receives 18 kilojoules of heat. What is the final temperature? So they are asking about the final temperature, and the given values are like the mass, which is given specific heat which is given. A temperature is initial temperature, I can say, is given. Heat is given, and they are asking about the final temperature. So we can simply put the values in the formula and calculate the final temperature. Okay, then. So here's the formula which says Q heat is equal to mass, specific heat, and temperature. This is the sign of multiplication. And we need to calculate the final temperature of this question. So yeah, I got the answer which says it's C. Okay, then let's see. So yeah, correct answer is C, which is 35 degrees Celsius, and the simple question to calculate. So here's the calculations in which we are given with the heat, which is 18 kilojoules. So we need to convert this kilojoules into the joules first, and by multiplying it with the 1000. And then we are given with a mass, which is 2 kgs. Specific heat, which is 900 joule per kg, because we are not changing the value of mass, because as we are given with the specific heat value, which is in the kg itself. And then we are taking the delta T, which is delta final and delta initial. So it's like delta T is Qm dot Cp, where Q value of Q is 18,000, M is 2 kgs, and Cp is 900. So after simply just calculating this, we get the 10 degrees Celsius difference. We are not changing the temperature into Kelvin because it is not required here, as delta T is already T final and T initial. So if we need to just calculate the final temperature, and for that we do not need to change the unit of Kelvin in that case. And this T final is T initial plus delta T. So T initial is 25 degrees Celsius, already given to in the question, and 10 degrees we get from the formula itself. So the T final will be the addition of these two, 25 and 10 will we get 35 degrees Celsius, which is C. So I guess it's a simple question based on this formula. These type of questions we can do by just remembering or memorizing the formula of these terms. I guess the concept of specific heat and this question is clear to everyone. If not, you can just write to me in the chat box. I will repeat the question again. Okay, then we will move forward with the next question. And this is the question, little bit not exactly tricky, but yeah. We can just, the steel block weighing 80 lbm is heated from 30 degrees Celsius by supplying 100 BTU of heat. What is the final temperature in degrees Celsius? So given as Cp of steel, which is 500 joule per kg per Kelvin. And also there's a thing which is given like 1 joule per kg Kelvin is equal to 2.39 of BTU LBM degree Fahrenheit. So they are asking about the final temperature in degrees Celsius here in this case also. So it's a similar question, but the thing is that the values, which is like 80 lbm and 100 BTU, which is given, is confusing us. But of course, we are also given with the fact that 1 joule per kg per Kelvin is equal to this. So we can simply convert or convert the units into one and can solve the question. Okay. I'm not getting any answer for this question. I'm waiting for 1 or 2 minutes more, then we will solve the question. I got the answer, which is 342.43 Celsius. We'll see that. Okay, I got 2B as answer. So yeah. Okay. Harris answer is A. We will check with the calculation because in the last question, as the calculation was little bit wrong here, also we can check with the calculations. So yeah, what's the solution? So in the case of CP, which is 500 joule kg per Kelvin, here we can simply change it to by multiplying it with this factor into BTU LBM degree Fahrenheit. So after multiplying, I hope this is the unit we will get. And the second step, because we need to calculate delta T. So for that, we use the formula which says it's Q. It's Q is equal to M into Cp into T. So here the value of Q is 100 BTU already is given, and the value of M is 80 lbm already, and we calculated Cp from here. So the formula should be look like this, and then after solving, the value is given as 10.46 degree Fahrenheit here. And because we need to calculate it in the Celsius, so they are calculating it in the Celsius by dividing it to 1.8, which says it's 5.81 degrees Celsius. So we need to check the calculation. Give me a minute. Yeah, okay. It's a little bit change in this factor, which is not, but into 10.46. If we convert it to degree Celsius, it will get, we will get a degree 12 degrees Celsius. And on calculating T final, it's a factor that 30, which is the initial, plus 12, almost. So the answer will be similar to 42. Yeah. Yeah. So the answer we will get is 42. Nearby 42, which is the option B, which is 42.4. So yeah, your answer is correct. B, 42.4. Answer will be B, 42.4. I hope this the concept or the calculations are clear to all. So some similar type of questions can come into the assignments. So you will able to solve these questions with the help of these formulas. Okay, then if yes, we will move forward with the next questions. So yeah, I guess most of the numerical based questions on conductivity, diffusivity, and specific heat capacity are done. And now we will talk towards a little bit into theory and into the polymers conductivity. So it's like first question is which factor most significantly limits the intrinsic thermal conductivity of bulk polymers compared to individual chains? So they are asking about like if it is an individual chain of a polymer or a bulk polymer which is the combination of many chains into it. So what factor most significantly limits or I can say decrease the intrinsic thermal conductivity? So among these factors, which will most significantly decrease the thermal conductivity? If we talk about the individual chain, so it is the individual chain of polymer. And if we talk about the bulk polymer, so they are like many chains which are aligned in any direction. So what is the phenomena which can limit the thermal conductivity of a bulk polymer? Okay, I got an answer which says it's A. We'll see that. Okay, I got A as answer. Let's see. So yeah, the answer is B, which is interchain van der Waals interactions. And the reason for this is just, yeah. And reason for this also, all of these I want to clear that all of these can limit the intrinsic thermal conductivity. All these factors decreases thermal conductivity. That's true, which is catalyst impurities, bypass stacking, cross-linking density, interchain van der Waals interactions, all of these. But the major contributor to limit the intrinsic conductivity is this interchain van der Waals interactions. And the reason for this is like in individual polymer chains, we can see that heat can be conducted efficiently along the chain due to strong covalent bonds, especially in well-aligned chains like polyethylene nanofibers. These bonds support phonon transport, which is the key factor to increase the conductivity, the transfer of phonons along the chain axis. But in bulk polymers, chains are randomly oriented and loosely packed. The interaction between chains is mainly through weak van der Waals forces, not covalent bonds. These weak interactions scatter phonons and disrupt the energy flow, leading to low intrinsic thermal conductivity. So if it in a single chain has high thermal conductivity, the overall bulk material behave poorly because phonon transport upon chain is inefficient. So the main reason for decreasing thermal conductivity in case of bulk polymers is their interchain van der Waals interactions, which can disrupt the flow of phenols. Cross-link density also can limit the intrinsic thermal conductivity. Pi stacking also limits it, and catalyst impurities also limits, because all these phenomena disrupt the flow of phenols. But the major contributor is B, which is the interchain van der Waals interactions. Okay, so we'll move to next question. So yeah, why do amorphous polymers generally have lower thermal conductivity than crystalline polymers? Either from the presence of alternating single and double bonds, irregular arrangement, increased phonon scattering, high bond energy of carbon-carbon backbone, and high crystallinity improve phonon travel. So what is the reason why amorphous polymers have lower conductivity than crystalline? Okay, okay. Oh, yeah. So what is phon? Okay, so it's like phonon, and phonon, I can say phonon is the particle which can transfer the heat or energy with them, and which is responsible for carrying heat through it. So that thermal conductivity depends on the phonons. It can be increased or it can be decreased. So yeah, in they are I can say the particles or the energies which is can carry the heat through one system to another system. And the answer for this is B, which is irregular arrangement, which increase the phonon scattering. So thermal conductivity in polymers primarily occurs through phonon transport, or I can say that they are the particles, or we can say there's energy which can vibrational energies which can travel, which helps to travel the heat with them through them, and which refers to movement of vibration to the material atomic lattice. Yeah, here also the definition of phonon is given. It says which refers to the movement of vibrational energy through the material's atomic lattice. So it's like the movement of vibrational energy. So in crystalline polymers, the molecular chains are arranged in highly ordered and regular structures, and which allow, like, these are the crystalline polymers, so one another the another chain and then another chain. So the movement of phonon from these chains are comparatively easy, and allow this allowing phonons to travel more efficiently with less scattering. Whereas in amorphous polymers, because of the random alignment of randomly or irregularly arranged chains, which create disorder in the materials and which disrupt the flow of phonons, and that's why amorphous polymers generally have lower thermal conductivity than crystalline polymers. And this disorder leads to increased phonon scattering, disruption in energy transfer pathways. So it's the correct answer, which says it's B, which says the irregular arrangement increase phonon scattering. The presence of alternating single and double bonds. This is the phenomena we can say which increase the electrical conductivity or the thermal conductivity also depends. But because of a single and double bonds, the reason for electrical conductivity increase is much higher. And like the higher crystallinity improves photon travel, this will not be the reason for amorphous polymer. And high bond energy of carbon-carbon back bond, this is not the reason why it has lower thermal conductivity. So it's the B, which is a regular arrangement which increase the non-scattering. I hope this is clear. Okay, then we can move forward to the next question, which is this. Which property of covalent carbon-carbon backbone in polymer contribute most to their mechanical stability? I can say the carbon-carbon backbone is not directly related to thermal, but rather carbon-carbon backbones helps or decides the mechanical stability of any polymer or any material. It's here the question depends on the mechanical property of the carbon-carbon backbone, which property will contribute to it. So high bond energy and directional bonding, presence of polar side group, alternating polar and non-polar bonds, and weak van der Waals interactions. So what are the properties which can directly impact the mechanical stability of polymer due to carbon-carbon backbones? Okay, so I got three answers, which says it's A, and is it correct? High bond energy and directional bonding, which is can influence the mechanical stability of polymers. So the mechanical stability of polymers with covalent C single bond C big bonds is primarily due to high bond energy because C single bond C is one of the strongest in organic chemistry with the highest bond dissociation energy of 348 kilojoule per mole. This makes the backbone resist to breaking under mechanical stress. And the directional bonding, which is covalent bond, are directional, meaning they maintain a fixed special arrangement. This gives the polymer structural integrity and resistance to deform, especially under load. So these are the two properties which together make carbon-carbon backbone mechanically strong and stable. So which is why materials like polyethylene, polystyrenes are so durable. So these are because of the bond energy and directional bonding. And if you look about the other options like presence of polar side groups, so polar side groups or the side groups do not involve much into the mechanical stability, and alternating polar and non-polar bonds are also not into the mechanical, and weak van der Waals force interaction, they can decrease the mechanical, not increase. So it's like the first one, the high bond energy and directional bonding, which will increase or which will contribute to carbon-carbon backbones and polymers. Okay, this is clear. We will move forward to the next question. We will have some similar questions like this, which related to polymers now. So in highly crystalline polyethylene, phonon transport can be very efficient because the polymer contains many chain ends, addition of plasticizers, presence of hydrogen bonding, or minimal defect and high molecular alignment. So why phonon transfer can be efficient in high crystalline polyethylene? I guess it's a simple question. Okay. We'll get two answers, which says it's C. So yeah, the correct answer is C, which is minimal defect and high molecular alignment. And this is the very obvious question because highly crystalline polyethylene, why phonon transfer can be efficient? Because of it has minimum defects and because of the alignment of molecules, the phonon transfer can be easily or effectively enough to increase the thermal conductivity. There are fewer defect and disruption in the molecular arrangement. Polymer chains are highly aligned, allowing phonons to travel longer distance without scattering. And the result is less phonon scattering, enabling more efficient heat transfer. And because if we look at the first, the polymer chain contain many chain ends, so this cannot be because this is not the phenomena why it is happening. Addition of plasticizers, so they can directly impact the crystallinity, not the phonon transport. Presence of hydrogen bonding, because it is a case of polyethylene, so there's no hydrogen bonding presence in between that. And the minimal defect and high molecular alignment, which is the reason why the phonon transport can be efficient. I hope these questions are clear to all because these are very simple questions based on the heat transfer of polymers. Okay, then moving forward to next question, we have like some more questions left, I guess. Yeah. A conjugated conducting polymer must have. So it is asking that what should be a conjugated conducting polymer? Polar side chains, hydrogen bonded between chains, alternate single and double bonds, or hydrostatic. It's a very simple question. Yeah. I got multiple answers this time. Okay, let's look at the answer. So answer is C, not A, not B, not D, because has a trick which says conjugated. And what is the conjugation? So conjugation is this, having a double bond and a single bond together. So it's like double bond, single bond, double bond, single bond. So they are the conjugated polymers. And these are the alternate single and double bonds along the backbone. They should have this to get the conjugation. And the conjugation can be due to either pi electrons or due to doped ingredients. So they are the reason why this conjugation. So it's an example of this polyacetylene. This PA stands for polyacetylene, which says that it's conducting polymers which have a single bond, then a double bond, then a single bond, then a double bond, then a single bond. So it should have conjugations. Conjugated polymers must have this condition to be in the conjugation. Polar side chains, it should not be a condition for their conjugation. High crystallinity, of course, they have, but this is not the reason why they are conjugated polymers, conducting polymers. And the reason for the conduction is also this double bond because so in these double bonds, and if you're talking about the electrical conductivity, because of these double bond, the flow of electrons are very easy among them and they will show the electrical conductivity. And as the line written, it's a conjugate polymer generally semiconducting without doping. So they are the semiconductors, like in the between of conductors and insulators, there's a term which is semiconductors. And yeah, they are the semiconducting when they do not meet doping. Is thermal or electrical conductivity? So this question is particular not on either of it, thermal or electrical. But right now, this question is only on the conjugated conducting polymers. So this is the majorly, if we talk about, they are talking about electrical conductivity, not exactly on the thermal conductivity. But the main point in this question is the conjugation conducting polymers. So conjugation is like the double bond, single bond, double bond, single bonds. And yeah, these type of conjugation helps in increasing electrical conductivity more than thermal. And the terms semiconducting and all this are related to electrical conductivity, not to thermal conductivity. That's true. Okay, then move to this question. I guess this is the last one or last second one, I'm not sure. Why do pz orbitals enhance electron mobility in conjugated polymers? So this question also belongs similarly to the next the previous one. So they are asking about the electron mobility here in the conjugated polymers, and they are asking why do pz orbital enhance? Either they form sigma bonds with hydrogen bonds, they overlap sideways to form delocalized pi systems, they increase hydrogen bonding, and they form covalent bond with oxygen atoms. So why pz orbitals enhance electron mobility in conjugated polymers? Conjugated polymers we have seen in the last slide, they are like this, double bonds with the double bonds, and because of these double bonds, it has a sp2 hybridization, if you talk in the terms of chemistry, which have one s and two. And why? Because the structure of s is like this, and the structure of p, because p has like x, py, and pz, three orbitals in them. So thus, if we draw on one axis, so it is px, if it is py, and this will be pz. So they are this, and the overlapping in this case, if we draw these structures like this, so these are the pi electrons and the p orbitals, and because yeah, all of you answer it as B, which is correct, because they overlap sideways to form delocalized pi system. And that's why the electron mobility in these double bonds is easier due to the presence of these pi bonds, which is the p orbitals overlapping. So the answer, this is the answer is conjugated polymers such as polyaniline, polypyro, polyacetylene. The key enhanced electron mobility lie in the presence of px, py, especially pz orbitals or adjacent carbon atom. These pz orbitals are perpendicular to the plane of carbon backbone, and when a polymer has alternating single and double bond, the pz orbital can overlap sideways. These sideways overlap create delocalized pi-electron system, allowing electrons to move freely, and that we have drawn like this. So this is the structure, so they can just simply, electrons can move through these delocalized systems like this very easily, and because of this pz, the sideways delocalized system can help in the electron mobility. So the correct answer is B, sideways to form delocalized system. Okay, so I hope this was the last this was the last question of this today's session, and electron mobility effect. Yeah, I can say that electron mobility and thermal conductivity are two different phenomena. There are many materials which shows electrical conductivity but not thermal, and there are many which shows thermal conductivity which do not show electrical. And the reason is because for the electrical conductivity, moving of electrons is an important phenomena, but for thermal conductivity, Phonons, or the vibrational energy which that can transfer from one form to another, is important factor rather than mobilization of electrons. So this can not directly impact the thermal conductivity, but this kind of arrangement, which is from the crystalline structure between them, can increase the phonon transfer or can decrease the phonon scattering. So ultimately can increase the thermal conductivity also. So yeah, in the structures like polyaniline, polypyrrose, thermal conductivity is more as compared to another one because of their structure. Okay, then I hope it is clear. So in today's class, we read about some of the terms like conduction in the solid systems, convection in fluids, radiation in the form of electromagnetic radiation. Then we read about the thermal conductivity, which says the ability of material to conduct heat from one system to another system, and then we read thermal diffusivity, which says the rate of heat transfer, like how fast the heat transfer from the system, which measure the thermal diffusivity. Then we read the Fourier number, and the Fourier number also measure the distance through which the heat passes. And then we read about the specific heat capacity, which is the heat required to raise the temperature of one unit mass of substance to 1 degree Celsius. So they are the terminologies, and then we read some questions over them. And this is the phenomena why thermal conductivity happens in polymers. I hope today's session is clear to all. And I wish you all the best for week 4, assignment 4. With these questions, you can easily solve the assignment 4, which based on the heat transfer in the week 4 system. Yeah. So I hope that's all. If anybody wants to ask anything about the previous slide, I can just right now go back to that slide and repeat. Okay, then if no, let's end the session of today's. I wish you all the best.